necessarily talking about those today, but mostly about things that we as computer scientists can address. So what I'm going to talk about today, for the purpose of this talk, blockchain is a data structure. So it's a chain of blocks. Essentially, it's going to be like a total order of blocks, most often a hash chain of blocks, such that there is an initial genesis block, and there are blocks that are linked. So maybe this block contains a hash of the genesis block, and so on. Sometimes the blocks are digitally signed, etc. So we'll see this. Each of these blocks contains some transactions. We'll see what these transactions are. But maybe most importantly, so if I have this data structure on my laptop, I still don't have a blockchain, right? So what I need is to replicate this data structure across a network of untrusted nodes. And then we are starting talking about blockchains. So essentially, you don't have a single node, you have a network of nodes. What does it mean untrusted? It means that they don't mutually trust each other necessarily. So so maybe node A trusts node B, but they collectively don't trust other nodes, or there is a setup in which no nodes trust each other, etc. Right? So you need to build protocols that will actually replicate this data structure, if you want, in this network of untrusted nodes. So what we typically use there are consensus protocols, and we'll see like which types of consensus protocols. Some are known maybe to computer scientists more than some others. But we'll try to see this during the talk. So essentially, what I'm going to talk about is going to give you the basis of Bitcoin. It's also going to give you also a bit of basis of Ethereum and of Hyperledger Fabric. I'm not going to talk about Hyperledger Fabric too much, so this is reserved for Wednesday for SRDS keynote. But I'm going to just briefly mention like what we try, so the shortcomings of the first two systems that we are trying to address with Hyperledger Fabric. So one question before I begin: how many of you know how Bitcoin works? Okay, and okay, fair enough. So I'll start from scratch. So basically, Bitcoin is the first blockchain system, if you want. So it has a specific application built in. So it has a cryptocurrency transfer. This is application for cryptocurrency transfer. It has a limited state-based scripting language with which you can customize this application, but you cannot program and replicate arbitrary application on top of Bitcoin. The consensus protocol that actually replicates that data structure across a network of untrusted nodes is based on proof of work. And we are going to see during the talk how proof of work works. It has a native cryptocurrency, well, obviously, and it belongs to the class of permissionless blockchain system. Then we are going to actually discuss some challenges that technologies like Ethereum faces. So Ethereum is more like an example system here. You can also put, for example, EOS, Cardano, and many other blockchains instead of Ethereum, but I put Ethereum as the first one, right? So what this class of blockchains tries to do, I put this as blockchain 2.0, it's trying to say, okay, let's not have a hard-coded application in our blockchain. Let's try to replicate an arbitrary application. So basically, let's build a system on which we can run arbitrary applications. So these are in the context of blockchain called smart contracts. And in Ethereum, you can code smart contracts in a domain-specific language. This is called Solidity. It also, so basically bold is new and what's not bold is not new. So basically this not bold stuff are essentially the same as in Bitcoin. So currently Ethereum relies on proof of work. It tries to transition to proof of stake, and we'll see also what this is, right? And this is for scalability reasons. And then it also has a native cryptocurrency, and it's a permissionless blockchain system. And then for Hyperledger Fabric, it essentially has many new things. In particular, we are trying to support execution of applications that are written in general purpose programming languages, as opposed to domain-specific language such as Solidity, so you can code your application in, for example, in Go, Java, etc. That the consensus that we use to replicate blockchain is not hard-coded and is not proof of work style, which will reveal expensive during this talk, so that you can actually plug in something more scalable. That it doesn't have native cryptocurrency, that you can have cryptocurrency as just another application, but if you don't want a cryptocurrency, you can actually deploy an instance of blockchain without it. And essentially, satisfying these requirements is motivated by scalability in one sense. So this is the part that I'm going to talk about today. But it also is motivated by, for example, different things like ability to program an application in general purpose language as opposed to domain-specific language, and ability to deploy a blockchain without a native cryptocurrency in the cases where you don't need a cryptocurrency, such as supply chain management and asset provenance tracking and things like this. And essentially satisfying this is anything but trivial from the computer systems perspective, which might not be obvious, right? So I'm going to talk about a bit of this today, but mostly in the context of scalability. But for a full-fledged talk on this, you need to attend the SRDS talk on Wednesday. So, okay, let's begin then. So I'm going to first talk about Bitcoin, but basically these are going to be focus of today's talk. So I'm going to talk about two scalability bottlenecks. One is this. So you saw that we have a total order of blocks in this data structure that's replicated. So the first bottleneck is actually how do we get the network agree on the order of blocks and the transaction in them across a distributed network. So this consensus transaction ordering performance is one of the bottlenecks that we are going to discuss. But then once you transition to actually blockchains that support execution of arbitrary application, there is another potential bottleneck there as well. And we'll talk about that. Essentially, you need to, in a scalable blockchain solution, you need to overcome both bottlenecks, because as soon as you have, for example, very efficient transaction ordering protocol, then this kicks in as a bottleneck and vice versa, right? So this is the application bottleneck and this is the network bottleneck, if you want. And in the rest of the talk, we'll see different mechanisms how to address this in the blockchain space. But we are first going to start from explaining how Bitcoin works so you understand what are the challenges. Okay, and in any case, so I guess we are a fairly small group, so you can interrupt me with questions. And if there are too many questions, I'll just stop this. So if you have any questions so far, please go ahead. Okay, so let's see how Bitcoin works. So essentially, we talk about this. So a bit, maybe I should just before I start say something about transactions. So transactions can be cryptocurrency transfers as in Bitcoin, but in the context of smart contracts, they can be inputs to the state machine or outputs of the state machine. So we'll see this, right, during the talk. Okay, so let's switch to proof of work and see how this chain grows, in particular in Bitcoin. So in Bitcoin, let's assume that the chain extended to the block 236, and we want to append the block number 237. So what this block is going to contain is the hash of the previous block. So this is essentially what establishes the hash chain, if you want. There will be a set of transactions, right? So in Bitcoin, these are cryptocurrency asset transfers. There are transfers from a certain Bitcoin address to another Bitcoin address, right? So far they are abstract, so this is just a payload. There is a root hash of this payload, so you build a Merkle tree on this set of transactions, and basically what we are going to care about is this root hash of the Merkle tree. There is the nonce, and there is the identifier of the node that's actually mining the identifier, so the public address that's controlled by the node that's mining this block. So the goal is to have essentially to find the nonce. So for every participant in the network called the miner, the goal is to find the nonce such that the hash of basically concatenation of all these fields is smaller than some defined target. So basically every miner tries to find the nonce such that the hash of the entire block, which is defined as concatenation of these fields, is lower than some 256-bit target. So how difficult is this? So basically, because the cryptographic hash acts as a pseudo-random function, essentially if I give you the target, and especially if this is a very small number that starts with many zeros, the best strategy that you have is to try nonce equals 1, and then you try the hash, and then increment. And if you don't, basically it doesn't hash, it hashes over the target, then you try with basically nonce equal to 2, and so on. So essentially, the probability that you find a nonce that is essentially lower than the target is going to be dictated by the target. And if the target is very small, if it's the number that starts in binary format with 80 zeros, then your probability is essentially 2 to the power of 80 that you're going to find a nonce that actually is lower than this target. So this is exactly what happens in Bitcoin. In Bitcoin, the target is dynamically adjusted by the network every 10 minutes by the hard-coded algorithm that examines previous block and defines the new target. This is done every 2016 blocks, and it's done in such a way that it maintains essentially the rate of generation of new blocks such that we have one block every 10 minutes. And essentially that currently means that the target starts with 80 zeros, which means that you need to, as a miner, you need to try 2 to the power of 80 nonces, roughly speaking, in order to find a valid block. So this is an astonishingly big number, right? So this is a crazy big number. So number of atoms in universe is 10 to the power 100, roughly speaking. And here you have almost 10 to the power of 80 for all practical purposes. You have like 10 to the power of 70 something, right? And that is essentially the protocol, like the core of the protocol, and it's crazy computationally expensive. So it's a very simple operation. So what you're just doing is putting a number there, you hash it, and you see what goes out. And it didn't work, and then you redo it again, and you redo it again, and redo it basically 2 to the power of 80 times per block. And this is where energy is wasted. But the protocol is very simple. Like, it's simple to explain, it's fairly simple to implement. I mean, the core idea of the protocol. And it's a fairly robust protocol because the attacks to this fairly simple protocol are kind of difficult to pull out, right? So there is not much you can do. But what of course can happen is that, for example, if me and Rui are miners, Rui can find a valid block with his nonce and his set of transactions, and I can find another block that basically extends the same block with a different set of transactions, different nonce and everything. So both blocks from all what I explained so far are valid, but then we don't have a blockchain. We have this fork here. So what's going to happen is that essentially this proof of work is not much of a consensus, right? It doesn't basically impose agreement across the entire network on the block. It just says that, like most of the time, because the probability is very low, we'll have one block at a time. So we will agree kind of for this block, and people will extend the same block. But every now and then, and this actually happens very often, we'll have actually two blocks extending the same chain. So what kicks in there is the second major part of Bitcoin protocol, is this conflict resolution mechanism, right? So the conflict resolution policy says that all miners are going to, so if a miner learns of two new blocks, it's going to store both blocks. It's going to actually, so now as a miner, I need to choose which one should I mine on. So shall I actually try to extend this one, or shall I try to extend this one? And the conflict resolution policy is, I will take the longest fork, which is not, this example is not good because actually the forks are actually of the same length, but in general is the longest fork. If they're of the same length, I will actually mine of one that appears more difficult. It's actually one that has a lower hash. So actually I will look at the hash of these two blocks and I will continue mining on whichever of them has a smaller hash. And that's it, right? So if all the correct nodes do this, and in principle, very roughly speaking, if you have a majority of correct nodes in the network, they are going to all apply the same conflict resolution policy. So they're going to all continue extending the same branch. And essentially, this is how eventually, this means that the branch on which the majority of the miners continued mining will prevail. So this also means one thing, that, for example, assume that you had that you provide some service and you were paid in Bitcoin, and assume that this transaction actually ended up in this block. But it is this branch that actually gets extending longer, and eventually this is the winning chain. And whatever you had, so whatever service you provided or transaction with which you were paid ends up here. this actually means that you were never paid, because the ground truth is the green chain and the green history. So which means also one other thing is if you apply proof of work to your blockchain and if your transaction is included in the blockchain, you need to wait. So you can actually not accept, you cannot assume that the transaction is going to stay in the blockchain just because it was included in a valid block that extends the current chain. You need to wait for a certain number of confirmations, and the number of confirmations heavily depends on certain parameters of a proof of work blockchain. So in Bitcoin, it's like taken that with large probability, large enough, right? So you can compute the probabilities depending on other parameters of the network. But the rule of thumb in Bitcoin network is that you accept the transaction as valid with fairly small probability of it being orphaned if it was confirmed by 6 blocks. So if there are 6 blocks extending this particular block, then with high probability, high enough, I would say, for this rule of thumb rule, you can assume that this transaction will stay in the blockchain. So now we come, and this is roughly speaking the whole explanation of the protocol, right? So you have the mining, which includes a lot of computational power. You have then gossiping of the mine blocks through the network. And essentially what you're doing is you have to be sure that you have actually transactions included and replicated across all the nodes in the network such that they stay in the blockchain like forever. You need to wait for certain number of confirmations, certain number of blocks that come after this block. So this method is very robust, right? So it works, and essentially you didn't have too many attacks on the Bitcoin network itself since its inception, with certain exceptions. But for example, whenever you see in the news that certain Bitcoin something was hacked, this is typically related to clients' wallets and exchange wallets. So this has nothing to do with the protocol itself. But what this means is that you have a very poor performance. So what I didn't talk about so far is that, so I talk about this. So there is one block every 10 minutes. So this is a magic number. You can ask why 10 minutes? Well, it's because the first inventor of Bitcoin, Satoshi Nakamoto, wrote this hard-coded in the code that it should be 10 minutes. And of course, you can change this if you fork Bitcoin code. You can change this easily. You can have your own blockchain with different block frequency. This is called block frequency. And the other magic number is block size. So it's what's the size of the block? How many transactions can you fit in the block? And the famous magic number of Bitcoin is 1 megabyte. So the payload, those transaction payload that I was mentioning, so this is 1 megabyte in size at most. So you can stuff only that many Bitcoin transactions inside. So typically the smallest possible Bitcoin transaction is around 250 bytes. Average transaction is more like 500 bytes. And then you can compute how many transactions go inside. But actually I will compute something else for you. With these numbers and the smallest possible Bitcoin transaction size of 250 bytes, this means that you reach the peak throughput of only 6 to 7 transactions per second. So this is an easy math, right? So one block every 10 minutes. In each block, there is 1 megabyte, which means with 250 bytes per transaction, and then it actually boils down to this. Latency, so what's the latency of the system? It's 1 hour. This is easy. So 6 block confirmations times 10 minutes. So to be kind of sure that your transaction stays in the blockchain, you need to wait for 6 times 10 minutes, 1 hour. And it has enormous energy consumption, right? So for me, this actually says 2 things. One is we need to improve this. But the second thing is it's actually the killer app that makes all the difference in the systems we build. Because if, like even in 2008 or 2009, if Nakamoto was not inventing the blockchain, but actually publishing the paper in SRDS, Eurosys, or any other systems conference, with these numbers, with high probability, the paper would be rejected, right? But it's the killer app that actually, so and the app is the worldwide censorship resistant money, right? It actually gives this blockchain to deserve another look at these numbers, right? So and the blockchain function, so Bitcoin is a blockchain function, but now in the last few years, as we transition to as the blockchain gain of popularity, these numbers did not make sense at all. So there is a lot of research, computer distributed systems research, to actually improving all these three numbers. So actually not to have these crazy energy consumptions, but to increase the number of transactions per second, both average and peak throughput, and to reduce latency. So just to put this in a ballpark, I mean, you all know about this crazy energy consumption of Bitcoin, but this site is essentially one that I like to cite. So essentially, this is 71 terawatts per year, like 8 gigawatts of engaged power. But these are like big numbers that we don't necessarily understand, even if you say the Bitcoin consumes more energy than Switzerland. So what I like is this, that this means that on average, you have almost 1 megawatt hour per transaction. And the average household in the United States actually spends less than that of energy per month. So for one Bitcoin transaction, this costs in the end more energy than the household spends in 1 month. So this is clearly ridiculous, right? And the reason it works now is it doesn't work because of transaction fees. So there are actually two incentives in blockchain that I'm not talking about necessarily today. These are transaction fees and block rewards. But this doesn't work because of transaction fees. Like nobody's paying fees per transaction that actually pay the utility bill of one household per month. It's actually amortized by block rewards, and these are at the level of 12 Bitcoins per block. So if you actually solve the puzzle and you mine the block, you get 12 Bitcoins, which is what amortizes all these costs currently. So it actually also gives a nice ground for research in economics related to distributed systems, because you have this economic incentive, you have basically Bitcoin as a blockchain working. And when you design a blockchain, you also need to think about these things as well. Okay, so let's move to how do we improve throughput, right? Throughput and latency. Essentially, you have these two magic numbers, which is the block frequency, how blocks you allow per, like how often do you allow blocks? No, it's not per second, it's like more like 6 blocks per hour. Can you actually play with this number? And there are many early variants of Bitcoin that essentially look at precisely that. So you may have heard for Litecoin and others, right? So Litecoin was probably one of the first to reduce this to 2.5 minutes instead of 10 minutes. And today in Ethereum, you have something at the order of 15 seconds per block. But this doesn't mean that essentially the latency stays at, for example, you reduce to 15 seconds, and then you say, okay, because I have 6 block confirmations, then the latency of Ethereum, for example, for the same guarantees as Bitcoin will be 90 seconds. So no, it's not. Because you have blocks more often, this essentially means that you have forks more often. And essentially means that you need to wait for more confirmations than 6 in order to have same probability of not reversing a transaction as you had in Bitcoin. So there is a nice paper by Sirjan Chapkun's group at ETH Zurich. So this appeared at CCS 2016, which essentially computes this for different values of these magic numbers and says that what's 6 blocks in Bitcoin is essentially like 37 blocks in Ethereum. This is not exact science, right? But it gives you the probability that's very close to each other. So this is more like 9 to 10 minutes. And this paper also says that essentially with playing with these two magic numbers, you can go from 6 to 7 transactions per second of Bitcoin up to order of magnitude more, so like more like 60 transactions per second. Let's round it up to 100 with this type of consensus mechanism. But because of the way wide area internet behaves, and because of the way this mining protocol works, this is essentially the limit. So if you have an application that's going to require more than 60 transactions per second or 100 transactions per second, you need to use different consensus protocol than proof of work. Yes. This class of protocol, it remains the same, right? So this was more like, okay, let's assume you can live with this, right? And then can you play with these numbers to actually get the if you want, so the rest of the protocols that I'm going to mention are going to address also the power issue. Right? So one of the proposed solutions in the permissionless blockchain space, like those that evolve from Bitcoin, such as Ethereum, is to transition to proof of stake from proof of work. So proof of stake serves two purposes. It serves to go beyond this bound of 60 transactions per second, and it also serves to move away from a computationally expensive and energy expensive protocol, precisely to answer Macedo's question. So basically to have a more lightweight protocol, if you want, in terms of computation. So how many of you have heard of proof of stake? Okay, even less. So proof of stake, what it says is essentially, so in proof of work, we had, you can view proof of work as a protocol in which the more computational power you have, the better the probability, the higher the probability you have to mine a block. So this should be obvious, more or less. So essentially what you are doing is some sort of weighted voting in which you vote with your computational power. So the more computational power you have, the more influence on the network you have, and more often can you put a block on the network. So what proof of stake says is a different thing. So you don't vote anymore with your implicit computing power, but you vote with essentially amount of cryptocurrency that you control, that's dedicated to voting and that you control. This can be something that this can be the amount of cryptocurrency you own, but in delegated proof of stake version, it can actually be delegated to you. So you all, like 1/4 of this room, can own some Ether and actually delegate it to me as a miner. So I will work essentially on the behalf of myself and this quarter of the room with all this stake and have higher probability of producing blocks, and then we somehow distribute the rewards among ourselves. Right? Okay, so this comes with its own set of problems, and it was announced in Ethereum in 2015, but it wasn't implemented even until today. And this is mostly because of a set of problems. Essentially, there is this nothing at stake problem that I'm going to explain in the next slide. There is an implicit concern about centralization. Now you're kind of allowing people that own like a lot of assets on the network, so a lot of cryptocurrency, to have even more power. So it's more it looks like rich get richer setup, but it's actually Bitcoin even suffers from this as well, because the miners are grouped into mining pools, and there is actually 2 mining pools that control more than half of the computing power in the Bitcoin network. This type of centralization is maybe not obvious in proof of work, but it actually happens in practice as well. So I'm going to talk about nothing at stake problem, which is going to explain also the trend where all these consensus protocols are going. So what's nothing at stake problem? So you remember our fork that we had from proof of work. Imagine now that you also are extending this, but you're not essentially mining, but you're voting with the percentage of your stake. And imagine that like 40, so I had a snapshot in which we have a fork, and 49% of the stake of the network is actually extending this one, and 49% of the network is extending this one. So it can happen in this can happen in proof of work as well. And let's assume that basically this 2% idle stake is assigned to this fork, and essentially this fork wins. So essentially I have a majority of the network now extending this. So in the long run, this fork would actually get longer. So far, this looks more or less like proof of work as well. There is one small issue. So what nothing at stake problem says is that it doesn't cost the attacker nothing to sit on 2 forks and actually keep extending this fork and keep extending that fork at the same time. And that's what's not possible in proof of work, because to be able to extend with the amount of computational power so I control X of computational power, and to have X assigned to both forks, it's not possible, right? Because this means that I control 2X of computational power. So I need to divide my computational power if I want to keep extending both forks. So essentially, I can assign 60% of my computing power to this and 40% to this, right? If I'm a malicious node. But if you're a malicious node in proof of stake network, it essentially just means that you are voting on both forks with your with the assets you own. So it doesn't cost you anything, and hence the name of nothing at stake problem. So which means that if you have 3% in this example of malicious nodes that are controlling 3% of stake, they can double spend, for example, by luring the network that this is actually the fork that wins, but then actually after they pass some transactions that they want reverted, they essentially assigned 3% of the stake to this one as well. And eventually this fork will win because it has more stake on it. And of course, I can make this more prominent by assigning, by having an attacker assign like that controls more stake. But I want to show you that it's possible also if you control like very little stake on the network, like this attack. So what this means is that, for example, this was recognized by Ethereum developers early on, but so that there is nothing at stake attack essentially makes the proof of stake which is built on a proof of work data structure. It makes it fork and basically makes consensus more difficult. So the solution that they have is essentially something that they're still working on, and it's called Casper Friendly Finality Gadget. It's a paper that was not published, but it's available on Archive. So if you're interested, look it up. But I want to only basically emphasize one thing. And the one thing is that what I want to do is they want now these nodes that are controlling stake to essentially go and do Byzantine agreement, finally, I would say, on those two blocks, and actually have an agreement among them which block is the one that extends this chain. And basically, if you're moving to proof of stake and you think of it as weighted voting, there is no, because of this simple attack, there is no other way but actually doing a proper Byzantine agreement if you want to solve this. So this is where it becomes interesting. So essentially, we saw how proof of work works. We saw that it hits the wall, even if you're if you want to accept the energy consumption, it hits the wall in performance very soon. So if you are from the permissionless world, you're thinking proof of stake or some weighted voting mechanisms, but they are boiling down to BFT protocols as well. And if you're coming from the permissioned world, which is what I'm going to talk about Hyperledger Fabric on Wednesday. So there we have node identities and it's not a permissionless network like Bitcoin. So there we start immediately from BFT protocols. So essentially in that line of research, this is how the two lines of research meet. And essentially what we are seeing now is that there is an arms race to a BFT protocol that can scale to hundreds of nodes and actually have a very good performance. So suddenly from a technology that like 5 years ago or 7 years ago when Bitcoin was not so known and the relations to BFT was not that obvious as it is now, when you were working on BFT protocols, this was considered exotic, right? So now, even if you're working on small scale networks, and now everybody wants networks of hundreds of nodes that actually implement a BFT agreement. So this is a funny thing about which research is relevant and which is not. Okay. So any questions by now? So I need to at this some point check the time, but shall I do a hard stop or I have more minutes because I started late? Okay. After that. Okay, so I won't keep you long. So I have actually many slides. I won't be able to talk through this, but I want to give you basically, so I want you to leave this talk with an overview of the issue, so to understand how certain things work and where we are going, right? Any questions? Okay. So BFT. BFT, how many of you know BFT? So I expect more things to, not too many, but at least some more. So this is a classical distributed computing problem, right? Where we want network to agree on a certain value, and essentially it's implementing illusion of centralized system that never fails, despite Byzantine. So Byzantine machine faults and network partitions. So what's a Byzantine fault? It's a model for malicious behavior, if you want. So when you see Byzantine, then you can just think malicious, and it's in the first order approximation is enough. Okay. So essentially, BFT protocols in principle disallow forks. So we saw this block being orphaned in proof of work protocol, but what BFT protocols allow you to do is essentially have no forks whatsoever, so long as the assumptions of the protocol are satisfied. Okay, so basically this talk goes now through PBFT, but I would like to, shall I do it or not? Okay, I can maybe do it, just to give you an intuition how this set of protocol works as well. It starts more or less like Bitcoin in a sense that there is one node that assembles the block of transactions. But then when it does, it actually assigns some metadata to it and sends it to others without any computation whatsoever. So maybe there is some digital signature appended to this block by this leader, but there is no 2 to the power of 80 hashes or nothing. So it just sends to others and says, you should include this block in your blockchain. And the guys basically say, okay, but we don't trust you because you might be malicious, right? So they exchange, they validate the block. They try to see which transaction he included in the block, but they then talk to each other to say, is this the block that the leader sent you? Is that the block that the leader sent you? So they try to basically get an idea what the leader sent to others. And for some reason, and I need 1 hour to explain you why, they need to do it once more. But once they do it once more, it's over. They can actually stop. And what the protocol guarantees is that if 2/3, so essentially there is some 2f plus 1 out of 3f plus 1, but essentially if the 2/3 majority of the network agrees that it's this block that the leader sent, now we can include the block in the blockchain. And that's it, right? So the good things is there is no exorbitant amount of computation going on, so you're not wasting energy as Bitcoin. What's also obvious is that we chat too much. So unlike in the Bitcoin network, we have some gossip protocol that's scalable, right? And we don't have certainly this amount of all-to-all communication going on. So what BFT, and of course there are BFT protocols that are less network intensive, but so they optimize for the network, like the number of messages on the network, etc. But what's like in general, if you have a BFT family of consensus protocols and proof of work consensus protocols, the first actually spends too much energy and wastes too much computation, whereas the BFT protocols typically more chatty. So if you have here a network of 6,000 nodes, like this all-to-all communication, and especially the first one in which you send the block to all, like this should be implemented by gossip or some more scalable protocol, right? But this is so what I'm giving you is the seminal Castro-Lisco protocol from like early 2000, when the technology was not actually meant for, built for the blockchains that are essentially hundreds of nodes. This was meant as a technology to replicate databases despite bugs. And then you replicated the database across 4 nodes and it was enough. So essentially we are sticking with these kind of protocols because they are much more power efficient and they allow us better performance in principle. Because so long as you can devise a protocol that implements this communication pattern efficiently, there is no essentially bound, like apart from the network bandwidth that's given to you on the number of transactions that you can pass through the network. If you think latency, like, and these nodes are scattered around the world, then you have essentially 3 message delays for latency, but 3 message delays even on wide area internet is the order of a second, right? Maybe a few seconds, maybe tail latencies are at tens of seconds, but they're not in minutes, and certainly not in hours. So this is why essentially I mentioned this, right? So BFT is known as a technology that matters for permissioned blockchains. It's where you know the identities of these nodes. And because of proof of stake and related approaches, it's becoming relevant to permissionless blockchains as well. So what you're seeing now in SRDS, actually, here's a few papers even in this edition on new BFT protocols. You see the arms race of implementing BFT consensus protocol that scales. And yeah, so essentially this slide summarizes proof of work with respect to BFT state machine replication. Here we can see that performance of proof of work is kind of bad. This is latency, peak throughput, power efficiency. It's much better with BFT protocols. But what's much nicer in this proof of work, and this is the reason it actually lives on and on, is the fact that you don't manage identities. And it's completely decentralized and completely open. Whereas in BFT state machine replication protocols, you need to have either the identity of nodes provided by some identity management service, or in proof of stake protocols, you have identities as the nodes that control certain addresses, which control certain number of coins. They need some sense of identity management. So we can say that we moved like from consensus that works on BFT consensus that works on very few nodes to say 100 nodes, but this is still being pushed further, right? So now you have basically you can even use PBFT style protocols that I showed you with more than few nodes, maybe up to 100 with certain fixes to the protocol. But you have protocols like in our last S2SP, there was a proposal to go to 500,000 nodes, etc. Right? But this is an active area of research. But in principle, it's not solved yet. So I used this slide for 3 years, but it's still valid, right? So if I give you the use case, if I give you the network, and I ask you, give me the consensus protocol that's most suitable for this use case, network size, whether it's like depending on different performance features of the network, most of the time the answer is not known yet. For certain classes of network it's known, but for most of the network it's not. Okay, and this is motivated in my paper that actually starts, so it has a title similar to this talk, the quest for scalable blockchain. The paper is from like 2-3 years ago. This should be updated, but it kind of gives you this overview of that I gave you so far, right? The proposal, some of the proposals actually are prominent, like Stellar, and the others are not yet prominent, I would say, but they are different. So if you want to go into details, go to this paper. So I would like to spend last few minutes on a different thing. So I promised, so this was the discussion about how to approach boosting consensus disordering performance and what are the bottlenecks there, right? So then I have a bunch of slides that describe, can we make the slides available? Can we make the slides available? Okay, so then basically in few slides I go and explain some of these proposals, but we don't have time for this, nor it's actually critical for the message I want to convey. But so what I want to say is that I want to mention this application. Yes, so I want to resume from here. So we said there's 2 scalability bottlenecks. One is related to how you do consensus, and there are these 2 camps like proof of work and BFT, and we said why BFT research is particularly important. It's both for permissionless because proof of stake, and permission because it was just BFT. But this sequential smart contract execution is very important as well. So imagine that. So what's happening in an Ethereum blockchain, for example? We mine this block. It's still proof of work. Remember, we mine this block, and then we have a gossip protocol over the network. And essentially, what every miner will do when it receives through the gossip this block, it also doesn't trust this block, but it needs to revalidate it. So revalidation is fairly simple for this very expensive part. So as the miner was mining to the power of 80 times, it finally came with this nonce. So to validate this is one hash verification. So this is very simple, right? So we just take the nonce that the miner found, and we are hashing it to see if it's smaller than the target. So that's one hash. But what's very expensive is that now every node needs to validate all the transactions in the payload. So what's happening basically is that if these are inputs to the smart contracts, this is the point. So when you learn about the block, you say, aha, it's the valid block because it has the right nonce. But then you go transaction by transaction sequentially, and you execute it. And what this means is that you need some mechanisms to, for example, to protect against denial of service. if you code an application that has an infinite loop, for instance, or just puts a timer here for 5 minutes and doesn't do anything and then it resumes, right? So you need mechanisms to either prevent this or to charge for this, right? So, and this is what Ethereum is doing, introduce basically to the blockchain scene, like both of these mechanisms. So one is that you cannot code whatever you want. You cannot code an infinite loop because there is a domain-specific language that actually forbids you from coding an infinite loop. There is the amount of time that you can spend doing things. So you can go and write to disk, I don't know what, right? And it's something that takes time and that blocks the performance of a blockchain. You cannot do, because what Ethereum network is going to do is going to charge you for every instruction of the code you're executing here. Like you want to access stable storage, it costs you that much. You want to do this type of operation, it costs you that much. So they actually come up with something that's called Ethereum virtual machine that defines a set of operations that you can do. And there is a price list. So each operation is charged that much. And the price list is, by the way, fixed across all nodes. So you cannot even change it unilaterally as you want. So it's the network that fixes these costs. And then you need to execute transactions sequentially, and you're charged for all these transactions. And this is mostly to prevent against denial of service. So this is where it becomes really interesting. So you have cryptocurrency is not only incentive for a blockchain, but it's actually a vehicle for you to fight against denial of service attacks. And you cannot get rid of it that easily, right? So this is the other part. So this should be advertisement for my talk on Wednesday, where I talk about Hyperledger Fabric, where we actually got rid of it. And you need to see, if you want to see how, and you now saw what, well, you can see why, but to see how, you need to come on Wednesday. Okay, so in BFT consensus, you can say, okay, we can use BFT consensus to actually not have sequential execution, and maybe it helps us. But remember, so this is where we stopped in the slide where I explained BFT consensus. And think about execution. Don't think about this ordering protocol. Think about execution now. It actually is the same. So what happened is that the leader transferred this block. We agreed on the block, and everybody appends this block to their blockchain. So what is this block? It's a set of transactions. And essentially, you need to do the same thing again. So we just changed essentially from proof of work to BFT. We changed the way we agree on the blocks. But what happens once we agree on the block is the same. You need to go sequentially, transaction by transaction, and do the execution. And essentially the same thing from the execution perspective. So it comes with the same set of problems related to denial of service, etc. Okay, so what time is it? Okay, so I have 5 minutes. So essentially, I'm going to finish by an advertisement for Wednesday's talk. So this type of challenge is specific to order execute blockchains. So this is where you apply a certain protocol, be it proof of work or BFT, to agree on the set of transactions, and then you execute these transactions in order. But what we did essentially in Hyperledger Fabric, and then this should be an advertisement for Wednesday's talk, is we changed it to another approach, right? And I'm going to come to that slide. But what this slide wants to say is also one other important thing. Order execute, if you want basically the state replicated consistently across the set of all nodes, works if what you're executing is deterministic. And this is another reason that essentially Ethereum has its own virtual machine and the domain-specific language that you code in, because they need to enforce that the application is deterministic. So if you have some crazy requirement like let's support general purpose languages just like that, without any other constraints on them, of course, I mean, you iterate a map in Go, it's non-deterministic. Let alone, let's not mention the cases where you invoke a random number, something that's obviously non-deterministic, right? But you basically iterate a map, it's non-deterministic. You check the validity of a certificate. This seems okay, except that it checks the system time. and system time is not going to be uniform across all nodes, and then it's non-deterministic. And actually, checking the certificate was one of the issues we had when we built the order execute blockchain. So this is why we had to change to something else. So enforcing determinism is a challenge, and these infinite loop applications that we discuss are the challenge, right? And these are the main reasons we needed to switch to something else in Hyperledger Fabric. Before I just give you this last slide, there are other proposals for scaling blockchains. So instead of, for example, having a single chain, basically there are proposals to accept different forks so long as you don't have a conflicting transactions across. For example, if these transactions on this part of chain are touching certain state, which is different from these ones, you can allow them all on the same blockchain. So this is essentially going to parallelization of sharding. So then you can execute these transactions in parallel. And essentially this is what we are doing as well. So this is the last slide. And this is what Hyperledger Fabric is doing. And again, the explanation is on Wednesday. So it's changing this order execute architecture to doing something else, saying we execute first, but then we do the order not on the inputs to the state machines, but on the outputs of the execution of the state machines. And then we validate the results. So this should be very much more lightweight than full execution. So what we have here is the ability to execute in parallel and the ability to execute non-deterministic code. Because once you do it, you can actually agree on the state updates that are coming from this type of execution. And then we do some deterministic validation here. But again, for details, I invite you to come on Wednesday. So I'll stop here. Yes. Yes. Mm-hmm.
Also you pay an extra price for the power, because now you have to execute things that you give up afterwards.
It could be, yeah. I mean, in a sense, yes, but all these powers are orders of magnitude less than what it actually hides in proof of work inside here, right? So it might be less efficient than execution here to a certain extent. I mean, you can still execute whatever you want here, and sometimes you will need to abandon it unless you have the way that you charge it through a cryptocurrency, right? But this is something that I would like to discuss in details on Wednesday. Yeah. So yeah, in the end, it might be less efficient than here, but this is orders of magnitude actually less important than what's going on here.
But my question is, how do you think this technology can be applied to this kind of time-sensitive systems, like systems, systems? Because obviously you have now a much more efficient way of stopping problems.
Mm-hmm.
But then you have to interact with the environment somehow. You have time-sensitive information.
Thank you very much. I mean, so blockchain is, of course, promising for everything, cure for cancer and everything. It's of course for cyber-physical systems as well, yeah. I mean, it is a joke, but it's actually, if you Google blockchain and cure for cancer, something will come up. Yeah. There's a question there.
Hi. Thanks for a nice presentation. I'm not very expert in blockchain, but I read that there's some applications that are time sensitive, like Mercedes blockchain. For example, transaction or banks or selling and buying shares. And so there's a question of if this approach is going to be applied, and to what extent. Your view on it. I mean, what do you think about? And since we are talking about changing money throughout the system, we have to worry about also for the synchrony, in a global time, I mean, and we have to worry about the scalability, as we talked about, and also with security. Do you think that this technology is going to be spread around the globe?
So let me answer the last question. There is no way whatsoever in near, mid future or far future that world reverts to the state of affairs before Bitcoin, so that nothing stays from blockchain. This like doesn't happen. We are on the downside of the Gartner's curve, so basically of the hype cycle induced by the prices of cryptocurrency around the last new year. So the ungrounded hopes are also coming down, which is good, right? Because then we see for actually what the technology is good. To answer your question, in protocols, so basically this three-phase gives you the lower, roughly speaking, the bound on the latency that you can have. I mean, you can optimize this. You can go in certain cases to 2 message exchanges, but this essentially gives you the latency when you ask about fintech application and banking application. You should think about this latency as the one that, can they support latency of few hundred milliseconds up to 1 second over wide area internet? Then the answer is they could use this technology. If you could also, by the way, deploy a blockchain network on a stock exchange itself, and then this is not a wide area network, this becomes a local area network, and this is like few milliseconds, or depending on how close they are, you can push this to few hundred microseconds even. So in that cases, yes, and there are many actually, at least proof of concept and prototype, but even some production deployments of distributed ledger technology on stock exchanges, where you actually want a highly performant BFT protocol or a substitute of it until we have actually one, but the latencies are fairly small. So security-wise, I mean, this is an overarching question. So all of these things are carrying. I mean, I can convince you that we care about security when we design things, but I expect so. Actually, stock exchanges and fintech, I expect them to be like. If you ask me what is the promising use case apart from fintech, that's more difficult for me to answer. But in fintech, it's going to something of this is going to stay for sure.
Thank you.
Are supposed to execute that information or not. They exchange that information, so they agree that that's the information that came from the leader. But how do you address the security of the leader? I mean, like, you have a list of the non-nodes, but how you can address the issue of the leader being copied by a malicious node, like?
Yeah, so at some point in this slide, I had a disclaimer, which I didn't go through. But it answers your question. I mean, the fact is that these protocols are much more complex than what I showed here. So I showed here the common case when the leader behaves well case, but actually, so when this is not the case, right? Then you need to implement leader election. You need to kind of detect that the leader doesn't behave well. This is typically through the progress. You hear that there are transactions, but nothing actually comes out at the end of the blockchain, so you're not ordering anything. So there are some timeouts firing left and right here, especially because the problem is impossible to solve unless you have the timers. This is the famous impossibility result from distributed computing theory. But all this reconfiguration and things like this is actually what makes these protocols challenging. I mean, it's not this pattern that I showed. I mean, it's this fairly simple. Yeah, it's a bit chatty, but it's still simple. It's actually all things that go behind the scene that I didn't talk about is what makes this difficult.
Thanks very much, Marko.
Só um aviso, os slides eu vou colocar lá no site do laboratório, vocês podem depois pegarem. I'd like to invite Professor Andrea Bonavalli now. And you, okay. And also